Bonjour à tous. On a le plaisir aujourd'hui de recevoir Svitlana Mayboroda, qui est à la fac liée à l'Université de Minnesota et le TH Zurich. Et donc, Svitlana a beaucoup de centres d'intérêt, l'analyse harmonique, la théorie géométrique de la mesure, les EDP, plus particulièrement les ondes incluant des aspects physique ingénierie. Et donc, on va voir apparaître tout ça, je pense, dans l'exposé qui parlera donc d'ondes en désordre et la loi du landscape, de l'horizon du paysage. Je ne sais pas comment on peut dire.
Paysage, oui.
Voilà. À toi, merci.
Merci beaucoup. Well, it's a great pleasure to be and speak here. Huge thanks, Anton, for inviting me. I'm very happy to be at the seminar and to see everyone and even non-local people that I haven't seen for a while. So as announced, I'm going to talk about the behavior of waves and disorder. It's a part of the huge project. I was asked to give more of a colloquium, or at least in part a colloquium talk, so it might be somewhat too general. You'll tell me. If you want any proof at any stage, you know, we can go for rectifiability and things like this. Anyway, so the content of the project at large is the behavior of wave disorder medias and all possible contexts of this. And one of the famous manifestations of this phenomenon is the Anderson localization, for which he got Nobel Prize 50 years ago. But our side of the field of localization, if you want, has started from introduction of what we call the landscape of localization, which is a very PD analytic object, a very PD approach to the subject. And in the intervening years, it turned out that the solution to somewhat unconventional in this field equation, H equals 1, where H is the underlying Hamiltonian, actually runs the show in a lot of ways. It provides both the geometric and the spectral information on disordered systems in particular. The pattern of the exponential decay, the rather precise prediction of the eigenvalues themselves, and the greater density of states. More recently, we started the conversation about the mobility H, the placement of Wigner functions, spectral functions. So I'll talk about all of that, or at least parts of that, throughout this hour. Oh, by the way, how much time do I have? Because I never actually asked. 50 minutes, hour?
About, yes.
And there are a lot of applications, in particular within the project, to systems of semiconductors, to cold atoms, to organics. So at this point, this is a part of big science collaboration on localization of waves. You can see 10 foundational PIs on the top, and the project itself includes about 67 people. It's hard to resist to mention that 2 of ours got respectively Nobel Prize and Fields Medal. You know both very well, I see. Alana Span, Hugo Dominirko. But let's pass to the science of it at this point. The experimental physics, the technology, is at the stage where we can observe and manipulate materials at the atomic levels. And in particular, here you see the snapshots from Alan's lab, from Bose-Einstein condensate, from Jim's back lab, from probe tomography, and the cartoon of organic semiconductor from Richard. But the point of the story is that at the microscopic level, materials possess an enormous degree of disorder, and you can see it in particular in this semiconductor. At the level of composition, at the level of geometry, of interfaces between the quantum layers, dielectric constant, you name it. And one could say that this material looks reasonably uniform from distance, what a little bit of disorder can do to a perfectly healthy LED. Well, from the point of view of waves, a lot, as a matter of fact. Let's recall how this goes. If you take no potential, so we look at the eigenfunctions of the Laplacian, if you wish. Here, let's say with normal boundary data on a square. The eigenfunctions are all uniformly distributed throughout the domain. This is what you imagine, perhaps, when you say the word wave. If you introduce a reasonably smooth potential, the situation is distorted, but not so much. In the presence of disorder, however, the situation changes phenomenologically, both from the point of view of physics and from the point of view of mathematics. The former sines and cosines become exponents and exponentially decay away from the small portion of the initial domain. And in terms of physics, a former conductor might become an insulator. Again, this particular picture, and there are many effects of localization, but this particular picture comes from the work associated to Anderson localization. And despite the fact that there has been about 50 years of development by now, very active development, both in mathematics and in physics, there is plenty of open problems at all possible levels. The experiments, they're usually hard to confirm, and more often than not, we don't know what we see is Anderson localization or not. In terms of theoretical physics, there are still critical exponents and mobility age and all of these effects which are of absolute importance and which are not understood yet. And in terms of mathematics, we basically still have only information about a few critical regimes at the end of the edges of the spectrum or for high disorder. And the delocalization hasn't been proved at all.
Are you going to give the definition of mu? Actually, did you say?
No. I mean, like here, this is associated to doped semiconductors, and this basically has to do with the critical constant for it. I can later on. I don't want to dive into this now. I mean, I won't discuss the critical regime as much, but I can. I mean, like we can discuss. So what's going on? Why is it so difficult to understand what's going on? Well, at the sort of naive level, we feel much better the behavior of particles than we feel the behavior of waves. Unfortunately, they behave differently. And in particular, if you have a square well, you can see here, let's see if this works. Yes, it does. So if you have a square well, of course, if you had a particle, it would be just sitting in the middle of it. If you have waves, they tend to go out, maybe not so much, they exponentially decay, they tunnel away, but they are still existent in the remainder of the domain. So they go where the particle would not, but actually the contrary happens as well, particularly in disordered potentials. In this one, so I'll be showing this picture a lot, so let's define it properly. It's sort of a classical, test picture. You take a square or a cube, you divide it into a grid, and you assign the potential to be 1, let's say, on black portions and 0 on white portion. So 1 or 0 at random, and then you look at the picture. Here, and in many of my pictures, intentionally, I take a bigger probability of 0 than of 1, so that you don't know that there is confinement. So the point is that it's very possible that the white part is propagating, and if you were a particle or you were a human, you would be able to walk through. The wave doesn't, or might not. In particular, here you see, this is the fundamental quantum state at the logarithmic scale. So it's not actually as large. This is a low scale. It's sitting somewhere here, which is very hard to quantify and explain. But the point is that the waves see something different than the particles do. And this is basically the entire premise of the project. It turns out that there is a certain hidden landscape, which we might not perceive. It's not the map of the potential. It's not the map of the material. It's really something born by the system, but yet it requires solving special PD, which nonetheless is sort of the world viewed through the goggles of the wave, in the sense that you can use it to predict and understand the behavior of waves, to draw these patterns of localization regions, even if there is no obvious confinement, to explain some other effects. And all this comes from a certain very PD harmonic analysis, if you wish, born approach to localization. So just a few snapshots of what it gave, and then I'll go in some more details. The landscape explains to you, and I'll tell you what it is. Again, it's a solution to HU equals 1, so I don't really have to explain. H being the underlying Hamiltonian. The landscape explains to you, gives you the map of the regions of localization. It sort of allows you, through a certain mechanism, to look at the map of the potential, compute the landscape, and then draw the regions where the waves are going to be localized. It gives the point control, which is, sort of first order of approximation, and then the pattern of the exponential decay through a more complex nonlinear mechanism. It gives you the energy levels, and I'll explain this in a bit more details, but sort of at the bottom of the spectrum, you can literally trace from minimum of the landscape the energy levels of the system, the eigenfunctions. That's at the bottom of the spectrum. Throughout the entire spectrum, it gives you the while law, and this is one of the main features of this particular talk is that for the first time we have the while law, which is independent on the energies. We have a result which is not semi-classical, which goes through the entire spectrum, contrary to the original while law and all the extensions that it has seen. It gives you further access to transport properties, to Wigner functions, spectral functions, some applications. Again, we are going to go through all of this. But let's do some math. So first of all, sort of the, not quite the beginning of the story, but the second beginning of the story was a realization that 1/u, so you take your initial Hamiltonian, Laplacian plus V, let's say V is a disorder potential. It can be a much more general Hamiltonian than that, but here that's our toy. You solve HU equals 1. And it turns out that you can rewrite the original Hamiltonian using a certain conjugation into a different equation where V disappears completely and 1/u, 1 over the landscape, becomes potential. Moreover, it sort of becomes the underlying manifold. So there are two terms, one which is sort of divergence form one. It's not literally the underlying manifold, but it's sort of the weight which defines for you the modification of the Laplacian, and two, the very same term ends up being in the potential. Now, you would say how this is any better than this? Well, the difference is that this is much better structured. And this crazy random potentials, the landscape has these features of chambers and walls and wells, which allow you to understand and to prove mathematically what's going on in much more clear terms. This is, of course, a non-linear transformation, which strangely sort of changes the world mathematically, since you're starting from the linear equation, and you would say it becomes more complex, and it does in a way, but it's also more powerful. Yeah.
So why the V on the right hand side?
Why there is no V on the right hand side?
Yes.
Do the same. I mean, like it's an explicit, you just, and that's sort of the point, that there is no V on the right hand side. The point is to make this random thing disappear. U is a solution to HU equals 1. So H is the initial Hamiltonian, right? So V is here.
Okay.
But in a very involved way. So it is, there is no loss of information between the two, which is sort of measured. But the information is encoded differently. Basically. So there is a way to see it through the edge and the dimension. I probably won't go through this in much more detail through the Rayleigh quotient and hard dimensions. Honestly, I never managed to make use of edge and the dimension. I mean, this ends up being a clear equation than the one I showed you, because this is an honest Laplace Beltrami. But edge and the dimension and localization is a major pain, because you're sort of introducing channels that were not there, and then you have to find them. But just for your information, there is a way to think about it this way. Anyway, long story short, from that transformation, you turn on the confinement diagonal machine, and you can prove that the eigenfunctions decay exponentially. I mean, this is the statement, as it has to be, because in this generality, you don't have pointwise control. But morally speaking, you prove that the eigenfunctions decay exponentially in the metric given by the inverse of the landscape. So you start from your equation. I'm generalizing here to dy grad plus v. You solve HU equals 1 or LU equals 1. You cut at the level of energy lambda. So you inverse it. You have 1/u. This is the map. You cut it at the level of energy lambda. And the moral is that your eigenfunctions are going to live in the wells below. And they're going to decay exponentially according to the maps of the walls around. And there is a metric associated to this, and you can prove the correspondence theorem. Yeah.
Just for curiosity. So what is the small parameter in the exponential decay? Because usually if you don't say small parameter, you just say anything.
It's not, it has to be, like smaller than the local spectral depth, in a sense. You need a bit of separation between the eigenvalues, and if you don't the separation between the eigenvalues, then your information will be about the layer, in a sense.
So U small in the regions.
No, U is not small.
So what is the
You mean, where is this delta coming from? Where is the small parameter?
No, because you have exponential.
You want to do the semi-classics? I'm not doing semi. There is no small parameter.
Exponential something. You want to say the region where the parameter is large or small, otherwise it's just constant.
I'm confused. Which parameter?
was fine. So
I mean, that's the entire point. There is no parameter in the story.
I guess the question is more exponential minus rho something depending on x can be translated into exponential minus x. Something like that.
You don't want to, in a sense. I mean, yes, you can. Using the PDM, you can say that 1/u is bigger than something, provided the original potential V is something else. So there are many situations in which you can. But the point is that this is a much more powerful information because, you know, if you are trying e to minus x, all you are telling me is that, you know, like if all these walls are higher than 5, then you will have e to minus 5x. That's true, but there is much more detailed information. So to give you a level of how detailed is the information, so in this potential, for example, this is the logarithm of the eigenfunction. So this is a map of exponential decay. This is the result given the landscape. This is e to minus 36. So it's not an identical picture, but it's pretty close. So I don't know, small parameter is e to minus 36, I guess, small in this picture. The restriction comes from Doug's computation. So if you want to ask why it's not e to minus 38, it's not a question to me. Anyway, so this is as far as the exponential decay goes. I won't give you the proof of this result, but I will mention that sort of mathematically speaking, this immense power of the landscape compared to just regular potential V in this particular setting comes from sort of perfection of the uncertainty principle. In which sense? Your eigenfunction, your wave has kinetic and potential energy. And the potential only encodes potential energy. But the entire point about the wave is that it has a kinetic energy too. This is exactly what gives you all these effects. This is exactly what lets it be not going through the same openings and yet be powerful enough to tunnel. The entire business about, you know, both tunneling and localization is actually about the interplay between kinetic and potential energy. And this conjugation rewrites it in the way in which there is much more weight in the new potential energy. Somehow 1/u, at least at the bottom of the spectrum, takes up the information from both kinetic and potential energy, mixes it up and gives you out something which is much easier to read. Because basically, at least you will see that this is not about the bottom of the spectrum, but I mean, I have to start somewhere. And at the bottom, this is the situation. The reduce the new kinetic energy and the new equation is much smaller, and the potential one sort of takes up the. So that's what's happening. 1/u basically encodes both sides of the uncertainty principle. With that, you can do, you know, what you imagine you should be able to do, which is, you know, you have exponential decay now, you can decouple the equation, you can prove the diagonalization. So what it means is that now basically you take the regions defined by 1/u, you take this new landscape geometry, you are patching up your space according to the landscape, and you can prove that the spectrum of the entire system decomposes into spectra of the small regions, basically with exponentially small errors. So it's a sort of diagonalization adapted to the operator. Once again, just to show you example of how it's going, you have your initial potential, you draw the landscape, you decompose it into what I call the value network, but that's again without going into mathematical definitions. If you think of this as a landscape, this is what values are. You know, I think in the pictures it's a watershed algorithm, but you know, mathematically this is below a certain level. And then you can see that the eigenfunctions religiously obey the values of the landscape. And as the energy goes on, some of them get erased because you're speaking of a higher and higher energy. Again, imagine sort of the water going through. And eventually you have some eigenfunctions which are going to be crossing, but all of this is still controlled by the landscape. So both this picture and this picture is born by one landscape computation as opposed to computing all the eigenfunctions. I'll just briefly mention that an analog of the sense, some of the sense now exists for the magnetic Schrödinger as well, which was sort of unexpected because, well, it's a complex equation. And these are very real variable results. So there is an analog of the uncertainty principle by student Breno-Poggi, analog of the corresponding exponential decay results. I will also mention that this went all the way to random matrices at this point. And in principle, while of course the Schrödinger operator can be in ZD at least, can be written as a random matrix, you would have the random potential on the diagonal and -1, -2 on subdiagonals. This is a very particular random matrix. In principle, of course, there is a world of matrices at large, and also the localization, but the game becomes slightly different, or rather the gist of the question becomes slightly different. What is the optimal width of the diagonal? In the sense that, you know, you take a matrix with random values, and let's say there are, you know, 2 W diagonals of random values, and the rest is 0, and the matrix goes to infinity. Then again, Schrödinger would correspond to 1 diagonal, which is random, basically. For full matrices, there is no localization. For Schrödinger, there is localization. So for which W does this stop? You know, there is a very clear passage. There is a conjecture which is n to 1/2, where is the size of the matrix. There are outstanding existing results, none of them coming close to 1/2 from approaching the question from both sides. But what I will mention is that, at least in the context of M matrices, which are those with off-diagonal elements, it basically means positive diagonal and negative elements otherwise, coming from, well, I mean, applications come from statistical physics, but I mean, it's an obvious object in mathematics. You can more or less run the same game. And this is a joint result with Marcel Filoche and Terry Tao. You can define the landscape analogously. You can introduce the matrix, which is, you know, it looks ugly, but honestly, it's sort of the same thing if you think about it in the discrete world. And you can prove exponential decay, and you get the right order of decay in terms of W. It doesn't prove the problem of localization for random matrices because there could be resonances. But it is a signature of the right order of decay. And already before us, there were a couple of results by physicists suggesting this, one in many body systems by Viktor Galitsky and his team, and one for Dirac-Hermans by Carlo Benacher, his pictures. But in the generality of random matrices, it's joint work with Marcel and Terry. And again, you know, there are pictures confirming that what we are saying is actually really happening, including the situation with random matrices, including the control of the width of the matrix. Now, going somewhat on in the direction of challenges and applications, as far as at least these geometric effects go, one of the major parts of this collaboration is the work with Alana Speth's team in cold atoms. And aside from getting the Nobel Prize, they have succeeded this year for the first time in observing the mobility age experimentally, or at least observing it sufficiently precisely that it does the computations.
I'm sorry, what is the mobility?
It's the moment question, and I should have said it. It's the moment when between localization, the threshold between localization and delocalization. So in dimension 3 and higher, all we in this random Schrödinger operators, from the bottom of the spectrum to, let's say, E0, everything is localized, and from E0 to infinity, everything is delocalized, or at least that's the conjecture. In the continuum, and if you are in ZD, then it would be symmetrized. But point is, there is an edge. It's not like localized, localized, delocalized. There is a phase transition. And this phase transition is a major question in experimental physics and theoretical physics and in mathematics, and we cannot even approach it because mathematicians basically prove localization at the very bottom of the spectrum, like epsilon 0. And not only we cannot say where the mobility age occurs, we cannot prove that it occurs in principle because nobody can prove delocalization. Diffusion is not accessible. We don't know how that anything is not localized. But you'd say, you know, like, okay, mathematicians might or might not, maybe physicists can. They can't either. And there is no effective prediction of where the mobility age is, depends on, you know, properties of potential, whatever it is. And again, experimentally, it is a major challenge to observe it because, well, this is experiment at the level of, you know, atomic systems. You need to really high temporal resolution. I mean, it's hard to see the moment when the quantum waves do something. So this year they have actually succeeded. I won't go with you through the results, but I mean, there are first experimental results which sort of satisfy the computational predictions. But what's more important for as far as this talk goes, for the first time we managed to predict part of it, and this is based on the landscape theory. So these are a couple of pictures. One for uniform potential, meaning you take values between 0 and 1 uniformly. One is for binary, meaning you take 0 or 1 by flip of a coin. The pictures are different. There is this famous diagram. If you haven't seen them, don't zoom in too much. But this is again, I mean, there is a transition between localized and delocalized regime, and these are the experimental, the black and the experimental data from different experiments and different computations. And same here. The percolation of the original potential, as you can guess, gives you exactly nothing. All potentials I've showed you, they are percolated. So the percolation of the original potential cannot possibly inform you on localization. As you know, as we discussed, this is not about classical particles. But the percolation of the landscape does. And if you take the landscape and you look at the percolation level, meaning at which lambda does it start, at which does it start percolating, surprise, surprise, it actually shows you the mobility. Now, this is physics. These are the results of Marcel's team. I have no clue why this is happening yet, but this is one of the major challenges, sort of one of the major discoveries as far as this year goes, from science point of view, if we don't zoom in on whether this is mathematics or not. But what do you do if you want to prove this? Well, step number one is you need to understand landscape as a probabilistic object. All theorems I showed you so far said if the landscape is like that, then the system, the exponential decay is like this, right? I mean, it's more like, look at the picture, there is a mountain, we will exponentially decay there. But when is there a mountain? So there is a question still of the connection between original system and what would be the landscape properties, probabilistically. And this is what brings me to also first results of this year, past year, depending on how fast we type, with Antoine and David. And we proved that independently sort of a probability distribution and these potentials, the landscape, I mean, we basically proved the first probabilistic results in this context, meaning that it's a proper unique stationary solution. It has exponential decay invariance, so the correlations decay exponentially, things like this. So this is first sort of the first groundwork towards the probabilistic properties of the landscape, and well, hopefully one day percolation results, just to let you know what one of the things that brings me here. But let's talk about the eigenvalues. So all of this was about eigenfunctions so far, all of this was about geometry. Quite magically, the same object also knows a lot about the eigenvalues. And the first observation in this direction was that if you take dimensional multiple of the minimum of one dimensional, independent on the potential, you basically get the eigenvalues almost on the nose as far as the numerics goes. Now, just to give you an example, again, same potentials as what I showed you before. The first 100 eigenvalues in blue, the first 100 minimum of 1 over u in green, the ratio is pretty close to 1.5, which is promised by this. And I have hundreds and hundreds of numerics like this. This is a different representation of the same numerics. So in 1D, you get slope 125. Blue. In 2D, you get slope 1.5. In 3D, you get slope 175 related to this prediction. So it's pretty close. And this is, the compilation of many experiments. I mean, this is sort of the average version. Last year, our students and postdocs proved the first theorems to this effect. They are still restricted to 1D and only certain systems. But they're basically showing that indeed at the bottom of the spectrum, you have this effect. And this has to be at the bottom, right? Because there are fewer minima than eigenvalues. I mean, if you think about this, you take a finite domain, there is a finite number of minima and infinite number of eigenvalues. And all of this is, of course, about infinite domains, but you are still going to be chasing your tail. So this is by design, bigger information there. But the landscape also knows things throughout the entire spectrum. And the way to do it is, the way to see it, is through an analog of the while law. So this is the original while asymptotic law, as all of us know it from, well, this one is not a 1924 version, but originating in 1924, which basically says that the number of eigenvalues below the level of energy E is roughly speaking the volume in the phase space. It's true asymptotically as E goes to infinity. It's not nearly close at the bottom. And for disordered potentials, it sort of misses all of the interesting information. In the sense that, so for instance, here you have one of these potentials that I was talking about. In blue is the actual while law, it's a counting function, that's why it's a step function. In green is the original while law. It will coincide asymptotically, but not in the interesting region. And the curious part is that if you substitute this potential for 1 over u, and you guess soon that this is our game throughout, you get the red line. So this is the original while law, this is 1 over u while law. It looks pretty close through the entire spectrum. And from this looks pretty close and many similar computations, 3-4 more years to make mathematics out of it, because as you say, what is the small parameter? What looks pretty close can possibly mean in the world where I'm emphasizing these are not asymptotic results, or at least I don't want asymptotic results. So what am I even measuring other than an eyeball metric? And again, there is nothing to sort of go from. You think, like forget the landscape, let's understand what has driven the while law to start with. The thing that my first intention, like many years ago when we first observed it, was to say, 1 over u is a nicer potential. But what nice actually means, there are thousands of results about while law. Very few of them even touch on the subject, how the error depends on V. They're all dependent on smoothness, but this is not about smoothness. So what nice even means? Just for your information, while law is wrong for even, harmonic oscillator, x1 squared plus epsilon x2 squared. Wrong, infinitely wrong, by factor of infinity. If you do the volume, it's going to give you an infinite one. It's just, so it's not about, complexity of the potential or something, it's just wrong. There is a Pfefferman-Fung uncertainty principle, which alleviates some of these issues, in particular, introduces the version which is right here, which basically says that instead of counting volume, you should be counting boxes of a certain shape. This is already better, but it still completely misses disordered potential, so it still gives absolute nothing on the ones that I'm talking about here. And then there are the so-called Lynch scale estimates, which explain what happens at the bottom of the spectrum for disordered potentials, but they're asymptotic at 0. And also very inexpensive. Fast forward some years of this, none of these two observations can possibly be, like very satisfying for physicists, obviously not right for mathematicians, so what's going on? So it turns out that there is an analog of the while law using the landscape. And to the best of my knowledge, this is the first version of while law which is not asymptotic, not dependent on any parameters. There are no small parameters in it. So the moral is you take your operator, I put no restrictions on the Schrödinger except for the fact that I can actually count integrated density of states, that it's a well-defined object. Solving H equals 1. And what I'm going to call is neither of what I promised you on the previous slide. It's actually the number of cubes of side lengths lambda to minus 1/2 on which minima are less than lambda. So in the end of the day, it is a certain counting function born by landscape, sort of incorporating a bit of this volume count and a bit of the minima count. And it turns out that with purely dimensional constants independent on anything, it gives you bounds from above and below, which for all practical purposes, for example, if u squared is a Dublin weight, and I won't go into what it is, but it mostly is. Certainly, if V is a disordered potential, it gives you bounds from above and below by just clean counting function. So there are multiplicative factors, dimensional multiplicative factors, which gives you the bounds throughout this, which give you the cube in terms of the landscape.
And then the cubes are cubes.
The cubes are cubes. So that's where, like if I really could get, that's where the dimensional things, that's because every time I double the cube, but the magic of, I'll show you, the cubes are cubes is a very good observation, and I'll tell you in a second, why and how, and why they're cubes. So as I mentioned, this is applied to any potentials. This does not depend on anything about the potential, not at infinity, nor not smooth, not anything, nothing. And it does not depend on lambda. It gives utmost precision in all these disordered potentials. It gives you the exact, Lipschitz scales as they're expected. If you are a specialist, you would care about fine things like logarithmic corrections. They give logarithmic corrections, so it's really, as precise as it gets. Compared to, traditional double log, which people can prove normally in this case. So this is much more precise. They also give precise constants. So one of the magics of the landscape, which is sort of how it always works in applications and something that we don't realistically yet see in theorems, is that it gives the correct constant. So one example is you take, just classical potential minus Laplacian minus k over x squared. By minus, I mean minus. So this part is positive, this part is negative. So at some point you switch from unbounded to bounded operator. And the switch can be computed explicitly. I mean, it's a 1D thing, so you can just do it. Well, this is not 1D, but you can separate variables. So the moment of switch is known. The standard while law misses it completely. It incorrectly gives infinity. So the standard while law is useless on this problem. The Fefferman-Fong one gives you not infinity, but a finite number, but it's not the correct finite number. And landscape gives it you correctly on the nose, the correct critical exponent. And again, landscape you compute explicitly here, right? It's minus Laplacian minus k over absolute value of x squared. So it's a, Mathematica can do it, but even I can do it. I mean, adjust an explicit formula. So it also gives correct exponent. I do want to show you, it's a long proof, but I want to show you just a couple of ideas, which also will address the question of cubes are cubes, I think, or at least what I believe is behind your question. So there are two things that work. There are two estimates, right? In one direction, there is a heavy use of this landscape uncertainty principle. It's the fact that 1 over u gives you a bound from below, and so minimum of 1 over u are the bounds from below locally on eigenvalues. So you take, you try to count eigenvalues. For one side, you take a space of codimension n, and you are looking for all of those so that this is bigger than mu. So you chop off into your cubes where minima are less than mu. On complementary ones, you use Poincare. On the ones not in F, you use this landscape uncertainty principle. But the point is that this uncertainty principle shows you that this is literally a bound from below. And that's why minima, always support your eigenvalues at least from one side, bounds from below, because that's. Now you would say this is not local, which is not, and that's where the other 30 pages of proof come from. But because landscape is a global thing, and so this would be all wonderful if everyone was supported in a small cube, but it's not that. But morally it's this. And the other direction, which makes cubes, is that because the landscape solves Laplacian plus v equals 1, and I emphasize because 1 is 1, you use Moser-Harnack, and you see that the landscape gives you the correct scaling. So what do I mean by this? It creates, it looks at this disordered crazy potential, and it's going to create for you the shapes that the eigenfunctions can take. It will make a cube into a cube. So what I mean by this is that you have this, crazy passages. If there is a space for eigenfunction in those, not the one that you see looking at the potential, but the one which eigenfunction would see, the landscape will modify this part to create a well of correct depths and of correct widths. And it's going to be, or it's going to be a collection of cubes according to the wavelengths. So it sort of alternates your medium according to the, to the scale, according to it's somehow a correct scaling locally. And you would say, I can also modify the potential doing that. You could, if the scales were the same across. They're different. Imagine your potential being much denser here than it is there. In this case, there is an infinite number of scales in the picture. So it sort of modifies correctly. It's like it sits at the point x. And it asks yourself, what the eigenfunction would see, what base in the eigenfunction would perceive locally at the space. And it creates a cube or a pole for the eigenfunction. And mathematically, this is because of this. This is because, this is the correct scale, and this one on the right-hand side, it sort of gives you the correct bumpiness, the correct shape for the underlying system. And then there is Spain. Where is pain coming from in this part? And the other part is from non-locality. And this part, when you do Moser-Harnack and things like this, you get twice bigger balls on the right-hand side than on the left-hand side, and that's inevitable evil. And that's also sort of a non-locality. And that's why if U is Dublin, or if covariance decay is exponential, like in the case of Antoine, things like this, you can use it. And if not, you have this correcting factor. So it's again from sort of restrictions of non-locality, but it's nonetheless pretty precise. In the last 5 minutes, the next thing to do. So now that you have energy information and you have geometry information, you want to have all of the information in the world. And all of the information in the world would be understanding really a phase space picture, is where wave is located on the phase cross space diagram, if you wish, or moment cross space diagram, phase space diagram. Because, well, energy is basically a projection on E. X is projection on X, but the wave is something that belongs to X cross moments, morally speaking. And if you have that, you have observations, so you have predictions of physical, quantum observables, things like this. So the way it is addressed is through the so-called Wigner functions. It is a formula, you have a transform here. Yet again, the moral is that this is sort of almost the probability distribution of your quantum wave in phase space. On one projection, it gives you Xi of X squared. On the other projection, it gives you Fourier transform, so energy information. And why am I saying it's almost a probability distribution? Is because it's not positive. So there is that. It can be negative. It is okay if it's modified with a proper Gaussian. But one important thing is that it preserves orthogonality of products. And so it almost paves the space. Because of preserving orthogonality, it means that it sort of paves you the space into locations of eigenfunctions, into the locations of waves, the phase space. There is a one-to-one correspondence between operators and Weyl symbols, the wave functions and Wigner functions, and more or less, you can view any value of your operator of your quantum observable through both mechanisms. How to predict Wigner functions? Well, or their locations for that matter. Because every operator can be viewed this way, in particular the energy, of course, which you can rewrite this way, which you can also rewrite this way. What am I trying to show you here? So this is an idea. It sort of tells you that PDF of E, PDF of energy, the location, the distribution, if you wish, is given by these layers where the Wigner transform lies between, the energy lies between K squared plus V. So it's as though it suggests to you that the information is here, that the probability distribution of energy is this. You know that it's not true because the value is not true. You know that your eigenfunction, the count of the eigenvalues, the Wigner function, the whatever else you want, cannot possibly be informed by just K squared plus V, because otherwise the value would be true asymptotically. And mathematically, well, this is an identity. Of course, the fact that two integrals are equal doesn't mean that two integrals. But now we know what game to play, and we exchange V for 1 over E. Notice that this is a much more sort of ambitious idea than the one in the previous ones, because again, the complexity grows. And we are not speaking of small eigenvalues anymore, and we are not speaking of the edge of the spectrum. We are not even speaking of the spectrum. We are speaking of literally predicting the quantum observables, all of them, at all energies. So this was Marcel's idea, and well, I didn't believe in it, I have to admit, but turned out no. Low energy, high energy, at least work numerically. So once again, you take the same operator, you take eigenfunctions, you compute Wigner transform, it's in color here. Sort of red and blue is positive and negative, but this is the Wigner transform. The black lines are the level lines of K squared plus 1 over U. What you're observing is that these contour lines predict the location of Wigner function pretty faithfully. So what I showed you before is this projection or this projection in some sense. What I'm telling you now is that it truly gives you a pavement of the phase space, at least numerically. Just to convince you that this wouldn't be the case for the original potential, although I should be pretty convinced now, there's a few examples. So this is the contour lines of the original potential. This is the contour lines of the landscape. Again, you can see that this is a much better predictable for the actual function than this. that the original potential sort of shows you too many features which are irrelevant. I mean, you cannot really say that this is informative, and same at the high energy regimes. I probably won't show, but I'll just go on and say that, you know, in terms of physics, the fact that we cannot prove it doesn't stop them. So we do have results, for example, for spectral functions in cold atoms, and this is in red are the experimental results of Alan's scheme. In blue are the localization landscape-based results, and in green are the best in classical predictions before. So the best before, you know, not so bad when you get to the classical regime. But for quantum situation, for deep quantum, for small potentials, you know, the landscape really does. Well, I cannot even say does much better. It actually does the job versus the green line. No. Now, mathematically, in my last 7 minutes, the thing is it's very difficult. It's very difficult to even approach. To give you an idea of what it is, the first result for harmonic oscillator we proved 2 years ago. It's literally for harmonic oscillator. When you look at the Wigner function, it's, you know, it's a complicated object, even in a very simple. So this is a square potential picture, just a square, you know, just one square potential. 1, 0, 1. Nothing, no disorder, no nothing. This is the tens, actually this is an infinite square, well, probably. This is the tens eigenfunction and its Wigner function. So what do you see? Well, you know what are the eigenfunctions of a square. Well, it's sines and cosines. The tens one will be, you know, respective sine or cosine. When you look at the projection on x, you see your sine and cosine. I mean, here again, blue is, I mean, I have to display it somehow. So blue is negative, red is positive. So the projection, I mean, read it as up, down, up, down, up, down. When you look at the projection, you know what is the Fourier transform, you know it too. But look at the complexity of the actual thing. And this is a square well, this is a sine and a cosine. What you can also observe here is basically I'm suggesting that, you know, the Wigner function is controlled by this level lines of the landscape or something like this. The level line here and the other one runs here. In which sense is it controlled? Well, the point, and this is actually explicitly suggested by Charlie Pfefferman, is that if you take a mass, so if you take an integral without taking absolute, then the mass would be really near this level of c squared plus 1 over u equals e. So the point is that the inside part is oscillating and sort of annihilating itself. And the sides are indeed, you know, the level lines are indeed what will give you the mass. But yet again, compared to everything I showed you before, to things like exponential decay, this is a much more delicate result because it's about oscillations. It's not about, I mean, if you go away, okay, it's exponential decay, maybe in some potentials, and you know, it's a robust effect. Here you have to take into account these oscillations, and the funny part, they are actually bigger. You know, if you take an infinity norm, the oscillations, you know, go up and down more. But they oscillate and they kill themselves very, very precisely, and that's what makes it difficult. So I'll show you first results towards this. Warning you, this doesn't look pretty yet. And I basically, you know, did the worst that any mathematician can do, which is spend 2 nights before the stop, you know, trying to shake out what I can squeeze out from the existing proof. In other words, proof what I can. This is a joint work with Stefan Decho, Jean Medias, and Eugenia Malinnikova from Stanford. And the first ones are our students and postdocs. And this is really the first steps towards it, but I wanted to show them to you anyway. So long story short, we have some idea where the, you know, why in principle the Wigner function navigates towards the levels of even c squared plus v. Again, let me remind you, the only existing results of a harmonic oscillator. So even having it for smooth potentials would be an achievement. So this is for now without landscape, we just look at the potential, we are just trying to understand the scheme. So first of all, the potentials in question are somewhat with controlled oscillation, but sort of BMO level controlled, not smooth ones. So what you are looking at here is, and what I claim is sort of defining the width of this layer for you. Because remember, I mean, I'm trying to prove that the eigenfunction, the Wigner function, navigates towards this level. But what does navigate mean? You know, you are trying to define a tube, right? So that the Wigner function is in there. What's the width of the tube? The thing is, it has to depend on x, and it has to depend on e. This is not a constant width. That would be stupid. Your potential oscillates. So what's the measure of oscillations? Well, this is a basically average. I mean, I'm writing it multiplying by the Gaussian at x of size sigma x, but this is basically the average oscillation minus the bar, minus the average. I do write here semi-classical H, but nothing depends on it. I mean, it's not a, well, or rather, I mean, everything explicitly depends on it, but it's not a semi-classical result. And what we are trying to say that based on, you know, sort of moving an x, you're moving an x-axis, you are looking at this, so this is your x, this is your c, your potential depends on x, of course. You are moving along x. At every point, you are looking at the oscillations of v in a certain, I'd say, be more like normal. Depending on this oscillation, you are defining for yourself the scale of uncertainty principle in a sense. So at this point, depending on this oscillation, you are finding the optimal radius of average. Sort of like landscape does, but again, we're not there yet. So you see the text, you look, you know, what is the reasonable radius to average zones here. You look and see. And then what we are proving basically is that, so this is the axis, but basically we are proving that the Wigner function projected on the space of Gaussians in a sense is bounded away from this tube. Again, I know it's not super explicit yet, but this is literally, you know, very fresh, so I'm not capable yet of saying it any more clearly. But the point is that every x, you look at the averages of v. It's not averages of v, it's averages of v minus the average of v. So it's a local oscillation, which has to be so, right? Because if your potential is whatever plus 5, this plus 5 shouldn't really matter. So you need to wash out the constant part of the potential. Depending on this, you have the scale of uncertainty principle. Using the scale of uncertainty principle, you're defining for yourself locally the balls, and they're different. The balls might be like this, the modes might be like this, depending on that. And then you are saying that your Wigner function basically has to be contained in these balls. Why am I writing it in terms of Gaussians? The Wigner transform, the Wigner function projected on Gaussians is positive if they are at the level of uncertainty principle. Otherwise, it's not. So it's by projecting on Gaussians that you see the mass. That's the point. I mean, that's why, you know, projecting on Gaussians makes sense. But basically, this was the first result in this direction, but I claim it will probably take another, you know, good 5 years to get there. But there is something. I'm trying to say that, you know, there is definitely something in this landscape approach, because this is what landscape will do. The landscape will average at the right scale. And I'll finish here. Thank you.
Thank you very much. Questions? Comments?
Yes, I go back to my question. So it's a very naive question. So if you just say like you give me an exponential function, the constant function, I see no difference. You don't tell me the region where you look at information.
I might not be understanding the question. You have an eigenfunction. It has integral 1 of c squared. So there is a number in it. If you tell me all numbers in mathematics are equivalent, I'm saying no, because the eigenfunction is normalized somehow. So the point is that having this number, which is 1, which is the normalization of your eigenfunction, the mass is in the very small region, which I quantify, and the exponential decay is away from this region. So if you wish, what I'm saying is that 99% of the eigenfunction are in a small region, and this is in an infinite domain. So it decays exponentially away from it. The speed of the decay is, you know, defined by the. So I think the magic number you were asking about is that the eigenfunction is normalized to 1. You know, integral of c squared is 1. So that's the point, that it lives in a very small region. I mean, like if you wish an L2 norm, I mean, like I like L2 norms because I work with d grad plus v, so they are not point-wise bounded. But in infinity norm, an L2 norm, and whichever norm you want, there is a small region in which it's localized, and then there is an exponential decay away from it.
So you mentioned the constant Kc or 1 over x squared. Is that constant come from the happy inequality, optimal constant?
I mean, this is a trivial easier than that.
Because
Yeah.
that's a change side of it.
Other questions?
Yeah.
Yes.
So maybe this is
everything unbounded sets, unbounded domains or not?
No, in the sense that, I mean, I personally always like to formulate sense on the bounded domains without dependence on the size, so that you can pass to unbounded when you can. So in particular, in these disordered potentials, the passage to unbounded domain is basically painless because everything is, you know, like exponentially deaf to each other in a sense. So this is more on unbounded domains. In general, again, when I say the results are true on all domains for all potentials, read it as follows. You take bounded potential and the bounded domain, and they claim that inequality doesn't depend neither on an infinity norm of potential nor on the size of the domain. And so if you can pass to the limit and that makes sense, then.
But then the last example about the harmonic oscillator, you meant the usual.
That's the usual. I mean, you know, this one, you know, like absolutely. I mean, this is amazing to me, you know. So the first thing they did that Hani and Zhao did more than 4 years ago. Laplacian plus x squared. You know, I mean Laplacian plus x squared. They have a more detailed information on the Wigner function. They sort of write, but remember they have explicit solutions. So you write them as polynomials. You use, you know, I mean, all explicitly, and you are putting the sense. And then they had the next paper, which barely came on archive now, already after Steve's death. I'm writing 22 as a dossier, but I mean, it just barely came on archive. I think there is just put it, is, you know, something that to me, you know, walks and barks like a harmonic oscillator. And the sense that they have a C-infinity potential with at most quadratic growth at infinity, with all convex layers, which are ellipsoid-like. You have an async result. So, I mean, this is slightly more general because you don't use the explicit solutions, but it's very, very, very harmonic oscillator.
Other questions, either maybe from the remote audience, I don't know. If not, thank you again.